There we go. So the recording started.
Shall we wait maybe 2 more minutes?
Yeah,
And it seems we are still missing the second speaker.
yeah, let me
Or
contact
do
them to make sure they.
Oh, Barry, Willie, are you coming to Berkeley next week? Yeah, now I see David. It seems David is also coming.
But so maybe let me just repeat the plan. So good morning, everyone. Thank you. Today we're doing something special, which is we're having a topical discussion on this topic of spin and hydrodynamics. And so we've invited two experts on this topic. So we'll have a 30-minute talk from Shi Pu and then a second talk from David Wagner. And then after that, we'll have time for discussion. So thank you to both of our speakers today, and thank you to Yi Yin for chairing. So I'll turn it over to Yi to introduce our first speaker, and we'll go from there. Thank you.
Okay, thank you. So welcome everyone. I guess we can gradually start. But before doing that, I think Pooh, can you try to just start sharing again?
Okay.
Okay. Okay, so can you make it full screen?
Yes. Yes.
And go to the next slide just in case.
Okay. Is that okay?
Okay, good. Good. I think yeah, it looks good. So can you go back to the title slides? I think we can start. And so as you know, I think today is like the 30 plus 30. So I might give you a reminder after 25 minutes because typically just to keep in time. And so welcome everyone. So let us begin by introduce the first speaker for today's topical discussion on spin hydrodynamics and heavy ion collisions. So our first speaker here today is Dr. Pu Si. So sorry, I think it should be Shi Pu. And so Shi Pu was got his PhD from the USTC in the 2011. And since then, he was doing the postdoc research, first in Asia in Taiwan University. Then he moved to the Germany he was awarded the Humboldt Fellow and doing the postdoc at the Frankfurt University. After that, he got the like PS Scholar Award and went to the Tokyo University as a postdoc. In 2018, he joined the USTC, University of Science and Technology in China, one of the best university in China as a junior faculty members. So as you might know, that Pu Si was working on things like the hydrodynamics, he derived some causality bonds related to the second order hydrocoefficients. He also pioneered the construction of the chirokinetic series dated back in the 2012. And he is still very interested in the quantum effects in the QCD plasma, the properties of the quark gluon matters in the external magnetic field and also on the non-trivial rotations. So today he will tell us more about some recent work on the hydrodynamics and spin. So now stage is yours.
Okay. Thank you. First of all, I would like to thank Daniel for the invitation and thank Yi for the introduction. Today I will talk about the thermal stability in the relativistic, viscous, and spin hydrodynamics. And this is based on the three work we have done recently. Firstly, I will give a brief introduction to the spin hydrodynamics and the journal discussion for the causality and the stability. So after that, I will implement the linear mode analysis to derive the causality condition for the spin hydro. So in fact, actually, we found some problem for the conditions. So that brings us another work. In that work, we use the thermodynamic stability analysis to study the spin hydrodynamics. So finally, if I have time, I would like to refer our new improved causality criteria. Finally, it's a summary and an outlook. So we know in the last century, there are two famous effects called the Burdett and Einstein-de Haas effects. They are the effects for the transformation between the rotation and the magnetization. The high energy vision of the Burdett-Einstein-de Haas effects has been proposed by Xingyan Wang and Zhou Tangliang. So for the relativistic heavy-ion collisions. So in the heavy-ion collisions, we know it can generate a huge global orbital angular momentum. And such a global angular momentum can lead to the polarization of the lambda hadrons and the vector mesons through the spin-orbit coupling. And in 2017, STAR eventually measured the global polarization of the lambda and lambda var hadrons. The result is also implies the quark-gluon plasma is the most vertical fluid which has discovered so far. There are many phenomenology models can describe the global polarization. As I show you here, there's many from there are a lot of work from many different groups. On the other hand, the local polarization has also draw a lot of attention. Recently, the work done from the Huichao and Ying Yi's group, and also from the Francisco Bertini's group, they proposed to add the shear-induced polarization to the local polarization. After that, this result can get a quantitatively or qualitatively result agree with the experimental data. So from the theory side, we can study this polarization phenomenon from the macroscopic approaches, which is we added the spin degree of freedom to the relativistic hydro. And while in the microscopic approach, we consider some quantum kinetic theory with the collisions, also with some effective theories. For the recent reviews, I refer to the reviews showing you here. So what is a spin hydro? Basically, the spin hydro are conservation equations for the total angular momentum tensor and for the energy tensor and the current. Usually, in a canonical form, the total angular momentum tensor can be divided as the orbital part and the spin part. So if we importing this kind of decomposition into this equation, we will find the variation of the spin tensor is equal to the antisymmetric part of energy moment tensor. So in that way, all of the three equations are coupled to each other. Moreover, the spin tensor can be decomposed as two parts. The first part, which is also considered as a leading order part, is perpendicular to the fluid velocity. And here, the S mu nu play a role like the density. So we call it as a spin density. It has 6 independent components, 3 for rotating, another 3 for the boosting. Then the other term is perpendicular to the fluid velocity. Usually we consider it as a higher order corrections. So now because we introduce something referred to the density, we have to introduce some quantity related to the chemical potential. So we introduce a spin chemical potential. And this kind of combination will also modify the thermodynamic relation. Actually, there are so many ways to derive the constitutive equation for the spin hydro. Different with a conventional hydro, we have some terms which is a Q and phi. They are related to the spin, the degree of freedom of spin. By using the entropy principle or from the kinetic theory, we can get the expression for the new quantity Q and phi. Here I will not talk about the details to derive it, but just I show you some reference here. So if you are interested, we also write a review paper. If you are interested, you can read these papers. Okay, you see now we have the basic theory for the spin hydro. What is next, right? So usually when we're talking about a relativistic many-body system, we have two fundamental requirements. The one is called causality. Another one is stability. The causality means the speed of the propagating signal cannot be faster than the speed of light. Then the stability actually means if we take the perturbation near the equilibrium, such a perturbation must decay with time, so that the system becomes stable. And usually, this analysis can be done in the so-called linear mode analysis. That is, for the hydro system, we can introduce the variation or perturbation to the independent macroscopic hydrodynamic quantities, like the energy density and number density. We consider the fluctuation of them. Then the whole hydro equation can be summarized into a linearized equation, which is shown like here. The phi stands for the variation of the energy density and variation of the number density, so on and so on. The m stands for the space derivatives. And moreover, we usually assume this fluctuation is a plane wave type, which is a constant time exponential. This is the simplest assumption. And once we inserting the assumption to the differential equation or the main equations, we will get some equation, and solve it. We will get the dispersion relation, which is omega as a function of the k. So the stability or the conventional stability actually means this imaginary part of omega should be smaller than 0. That is, you see, if the imaginary part of omega is smaller than 0, these modes will be decay with time, right? So that means it's stable. So causality actually means if we compute the group velocity of this group velocity should be smaller than 1. And that is also very physical, right? This is a very simple standard, a very simple requirement, but it's very useful. The one thing is, at the very beginning, there are a lot of discussion for the first order hydro. You'll find the conventional first order hydro is always a causal and unstable. Then that is why the current relativistic hydrodynamics has been extended to the second order, like the MIS theory, BRSS, or BDNK series. Of course, there is another way, which is a generalized first order causal hydro, or namely the BDNK theory. This is a kind of solve the problem for the causality. Another one is once we have this causality or stability condition, we can get some constraint for the transport coefficients. If we have a viscous hydro, we can get the constraint like the shear viscosity at the relation time for it should be satisfied this inequality. This inequality is indeed solved from the causality or isotopic causality condition. So that actually gives us some limit to choose the parameter when we take the simulations. So that is another kind of application for the linear mode analysis. Then we have the theory, we have the method. Then we just combine them together to say what happens if we implement the causality condition or analyze for the spin hydro. And this work is done by incorporation with 3 students. This is Xin Qing, this is Chen Yang, and this is Dongling Wang. So we consider the fluctuation of energy density, fluid velocity, and the spin density. So we get this kind of a big linearized equations. Then we solve the dispersion relation. In the first order, we find the omega can be proportional to the k square, or k powers 4/3. So this actually breaks the causality criteria, because if we take omega over k, could be infinite when k goes to infinite, right? So that is a causal. But this is not a surprise. As I said, the conventional first order conventional hydrodynamics is also unstable and causal. So that is not a surprise. The thing is, we need to extend it to the second order. And there is many ways to extend the second order spin hydro. For example, from the entropy principle or from the kinetic theory. I think David may give a more detailed discussion on this side. But now we are concentrate on the causality problem, right? So there is one standard way to extend it, called the minimal extension to the second order hydro. So the key to get a causal usually means we can add a relaxation time for the corresponding dissipative effect. So in this case, we can just add the relaxation time for the Q and phi, which is related to the spin evolution of the spin. Then we get the so-called minimal extension, second order spin hydro. So let's see what happened. So firstly, we immediately get the causality condition. This condition is simple, but looks a little bit complicated, but we can get it. And we have tested it, it works well. But the problem is once we move to the stability condition, we derive this inequality in the large K and the small K limit. It looks okay, right? But when we do some tests, we plot the imaginary part of the omega as a function of K. We find out in the small K or large K limit, this equality can guarantee the state stability. But for the final number of K, actually the omega can change the sign, like I shown here and here. So that means the system become unstable, even the stability condition is satisfied. So that is very strange. Of course, there are several different reasons. One possible reason is the conventional stability criteria may fail. Or another one is maybe we construct the spin hydro in a wrong way, right? We don't so far. When we're doing this paper, we don't know the exact answer. So that brings us we need to go to test it, go beyond the linear mode analyze to say what happened. So that is another work is we analyze the stability by the so-called thermal stability analyze. And this work is done in cooperation with my student Xiang Ren and also with these two students. So what is the thermal stability? Roughly speaking, thermal stability actually is the second law of thermodynamics. For example, if we can consider a fluid, a huge, big fluid, and we pick up one small side, one small piece, which is a fluid cell. Because this fluid is so huge, we can consider it as a thermal bath. Then this fluid cell shares some temperature, chemical potential, even the fluid velocity with the thermal bath. And the second law of thermodynamics actually means the total entropy of the whole system should be increased, right? That is very physical. And then the variation of the entropy can also written like the combination of the conserved quantity times their thermodynamic conjecture, which is a Q and alpha. So Q, you can consider Q like the number density or energy moment tensor. The alpha stands for the chemical potential or the temperature velocity. It always compile together to give the variation of the entropy. So when we can do some very simple algebra, we rewrite the entropy variation of entropy for the thermal bath by this equation, right? This is just replace it. Then because the Q stands for some conserved quantity, so the total, the bath part plus the hydro part should be totally conserved, right? So then this part can be replaced by the minus Q for the fluid cell. And because the fluid, the whole fluid is so big, or the thermal bath is so big, so they share the same chemical potential, temperature, so on and so on. So we can roughly replace this alpha for thermal bath by the alpha for the fluid. Then you see the total entropy, variation of total entropy actually become the variation of the fluid entropy plus all the quantity for the fluid cell. And this is this inequality is equivalent to the second law of thermodynamics. And then in this paper, people introduce a new quantity called the information current. This is the information current. And if we integration the information current with a hypersurface, which is cover the fluid cell we pick up, the entropy principle, this equation will be replaced by this new one. This required integration should be larger than 0. And mathematically, this inequality will give us 3 conditions. One is if the E times N should be larger than 0. The N actually is a future directed normal vector for the hypersurface. And this can be equal to 0 when all the perturbation goes to 0. And the space-time variation of the E should be smaller than 0. This 3 condition is equal to this one, and also equivalent to the second law of entropy of thermodynamics. So that is 3 equation we call like the thermodynamic stability conditions, and it had been proposed by the Gavin-Nelson paper in 2022. So let's take a comparison between the new thermodynamic stability analysis and the linear mode analysis. So this thermodynamic analysis coming from the second law of thermodynamics, but the linear mode analysis actually is depends on the causality and stability from physically, right? And here we are looking at the information current. But for the linear mode analysis, we'll focus on the plane wave type perturbation for simplification. Their criteria also looks a little bit different. But on the other hand, if physically this thermal stability analysis is more general or more does not depend on the plane wave type perturbation assumption. Right? So let's say what happened. Here, firstly, is an example. We consider a full relativistic viscous hydro with a viscous tensor only. Then we can compute the variation of the hydrodynamic quantities. We compute this kind of information current times this norm vector and mu. And interesting, you find first this kind of expression, including the variation of the shear viscous tensor, and it's squared. So that's totally is a power of delta squared. In comparison, in a linear mode analysis, we only focus on the linear terms for the perturbations. But here, this is a second, it's a perturbation square. So that is one difference. Another thing is, if you require this one larger than 0, this is very simple because all of these are square. So that means the coefficient here, all the coefficients should be larger than 0. And we get some expression here. And interestingly, this kind of requirement is exactly the same as the causality and the stability condition derived in the linear mode analysis. So that gives us some information. That is, this kind of thermodynamic stability analysis is workable, at least for the viscous hydro, right? But what happened to the spin hydro? Honestly speaking, this result is this calculation is not difficult, but a little bit complicated. The student spent more than half a year to simplify the expression. Eventually, they got some inequality like this. So if we compare what we have derived here to the result derived from linear mode analysis, we find out the above condition can give the causality condition for the spin hydro in a linear mode analysis. So this is always okay. But for the stability condition, we find out the thermodynamic stability condition actually is more stringent than those derived for the linear mode analysis. So that's kind of a new condition can help us to avoid the puzzle I mentioned in the last section. So somehow I think this puzzle for the spin hydro is partly be solved by the thermodynamic stability analysis. Okay, so then I think I still have a few minutes. Let me talk about, we propose a new improved causality and stability criteria in a linear mode analysis. This work is in cooperation with my student Dongning. So if we look at the conventional analysis in a linear mode analysis, there are 3 problems. The one is, usually we do the analysis in one frame, for example, the rest frame. Then we transfer everything to another frame. This kind of process sometimes become burdensome. It's not hard, but just complicated, and it's hard to get the equality. So that is one challenge. Another thing is, recently people have found the conventional causality criteria actually is incomplete. after a few slides, I will give you an example, and that is to show you why it's incomplete. And there is another question, or physical question. So what is the relation between the stability and the causality? So what is the relation between them? But interestingly, in 2020, Gabinotino, he published a paper in PIX. He gave some physical interpretation between the causality and the stability. So causality actually means everything or every event happened inside a light cone. And a causal means the event or signal transfer out of a light cone. So let's say if we have a fluctuation and t equals 0, then after some time, the fluctuation is gone, and later time, t, of course, t should be larger than t0. So if this happened inside the light cone, we can do some nodal transformation. In any frame or any physical frame, we always observe the fluctuation decay with time. But if in one frame, this fluctuation propagating outside of light cone, then after some nodal transformation, this t could become smaller than t0. Physically, that means we observe in a very special frame, the fluctuation increase with time. So that is unstable. So as a consequence, the causal propagating means unstable physically. So this is a very nice physical interpretation introduced by the Gabinotino. But how say it mathematically? That is one problem, right? Another thing is very recently, in the last year, the two groups, one is from Haller and Cooperator, and Gabinotino, they propose an improved stability criteria condition. Firstly, they let the propagating wave number be complex. Then they require the imaginary part of omega should be smaller or equal than the absolute value of the imaginary part of k. Firstly, you may wondering why the k could become the complex. Usually the wave number is always real, right? So the reason is like this. Assuming we have a system and in one frame it is stable, then that means we have the imaginary part of omega. Then we do a nodal transformation, omega k to omega prime k prime. Now k prime actually should be the function of original omega. So the k prime is imaginary. That means if we consider nodal transformation, it's natural to choose the complex k. So that is a new stability criteria proposed in their papers. And then in our paper, actually, firstly we proved if this kind of a criteria hold in one frame, it can hold for any frame. So that is it's very good. So that means you can do everything in one frame. That is enough to guarantee the stability. So moreover, we propose a new improved causality criteria. Here I just introduce you the simplified version. That is say, for the system, if we have found a constant b prime, to let this inequality be satisfied, then the system is causal. And if this equation or inequality is satisfied in one frame, it will be hold true for all frames. So that is the new causality criteria we have proposed. Here is one example. There is one famous dispersion relation, which is omega equal to k times 1 plus I over 2. So if you use a conventional one, you take the omega over k, you'll find this is 1/2. Of course, it's smaller than 1. It looks like it's causal. But if we use a new improved one, you will find, let's say if we set k be real, then imaginary part of omega, just the k over 2. And this requires k over 2 be always smaller than constant b. But we know k can be infinite, so we cannot find a constant number k, b prime to satisfy this kind of inequality. So that means this dispersion relation means a causal. So that is, but on the other hand, mathematically we know this famous dispersion relation is a causal. And that can have already been proved mathematically, as shown in this mathematical books. So from this side, we know the new improved causality criteria actually is more stringent than the original one and could work better than the original one. Another thing we have found is if we put the stability criteria and our new improved causality criteria in one single frame, in one single figure, this is imaginary omega, this is imaginary k, we will immediately find out the relation between the stability and the causality. That is, once the system is stable, it's always causal. That is what we have derived from this kind of figure. So somehow this is answer the question, the relation between the stability and the causality, linear mode analysis. After that, actually, this is not the end of the story. I have to say it's just the beginning of the story. Because so far, there are 3 different groups, including us. We proposed 3 different causality criteria. One is from Hiller and Gavinasmo, Daniel George Noraha's group. Another one is Kofton and his postdocs group. You see, the 3 of us are a little bit different. So the next question is, which one is better? To this question, I don't know. I have to say, more systematic study is needed for your future. Okay, I think I have to talk about too much, so I have to summarize here. We have studied the causality and stability for the spin hydro, and we derived the causality condition and find the conventional stability criteria field for the final wavelength limit. Therefore, we analyze the system by the thermodynamic stability analyze, and which gave a more stringent condition compared to the one divided in the linear mode analyze. And last, we introduce a new improved causality criteria, which we find the stability means the causality in a linear mode analyze. So that is all. Thank you for your time.
Okay, yeah, thank you so much, Pu, for the presentation. I think we will defer all the detailed discussions after the second presentation, but if there's an urgent question, so please speak out. Just urgent and short question, any? If not, and David, can you try to start sharing your screen? Yes, thank you, Pu. And now
my PC decided to freeze on me, but Francesco was so kind to let me use his. So I will now try to talk from here. So I guess the whole screen. And now. So can you see it?
yeah. Right. I can see it, but can you try the full screen?
Okay, perfect.
Can you go to the title slides?
Yeah, that should be the title, right?
Okay, great. So so before David start his presentation, I would like to give you brief introductions. And so first of all, we actually need to congratulate David Wagner, who just got his PhD from the Goethe University. And he just moved to the University of Florence as a postdoc working with the Francesca Baccattini. I should say really remarkable that just within the last 2 years, David published a number of interesting papers on the physics related spin hydrodynamics and heavy ion collisions. For example, he presented the quantum kinetic theory description to describe the vector mesons, which is also which has also attracted a lot of attention, both theoretically and experimentally. He also the one of the 2 papers who first proposed that shear may also introduce the vector meson spin alignment. He also had a very nice piece of work on deriving the spin hydrodynamics from the kinetic theory with very non-trivial collision kernels. And today, David will tell us about the damping of the spin waves.
Okay, yeah, thanks a lot for the introduction, and also thanks for inviting me to talk here about our recent work on the damping of spin waves, which was in collaboration with Masoud Chokri and Dirk Grischke. And also thanks to Francesco for letting me use his PC here. I'm still getting used to my new office in Florence. So okay, then I would say let's start. By the way, can you see my mouse?
I can see it's moving.
Okay, perfect. Okay, so some things we already have heard in Shi Pu's talk. Some things will be new, but I'll start with the introduction anyway. So in heavy ion collisions, we can measure several observables related to the polarization of the emitted particles. And the most famous one is probably the polarization of lambda baryons. And of those observables related to lambda baryons, the most famous one is probably the global polarization, which is also measured first. And what's going on, you can see here pretty well in this cartoon here. We have a non-central heavy ion collisions. There's some non-zero input parameter B. And now one would think that intuitively, okay, if those heavy ions have some finite distance with respect from each other, then the resulting medium in the middle will get some orbital angular momentum, which in this cartoon here points in the negative y direction. And then one can think of solid state physics and what one remembers from there, namely of a specific effect called the Barnett effect, which consists in the fact that if you take a magnet, a ferromagnet, and you rotate it, you will see that the magnetization of this magnet increases. And this is depicted down here in this cartoon, and it's simply an effect of the fact that the spins in this magnet align with the axis of rotation. And so from this analogy, you would expect that you can also measure the polarization of the emitted particles in the direction of the orbital angular momentum. And indeed, that's what happens, as you can see on the upper right. So to lower energies, we have a very non-trivial signal here. And indeed, this can also be explained quantitatively by assuming some hydrodynamic models, and mainly by assuming the spins of the particles to be in equilibrium. So in this way, we have simply polarization through rotation, and everything seems to be fine. But unfortunately, it's not exactly like that, because if we go more differentially, things become a little worse. Another observable here is the so-called local lambda polarization. In this case, we are interested in the polarization not along the orbital angular momentum, but along the beam direction, which in this cartoon would be the z-axis. And we would expect that we see a signal there as well. Because of the expansion of the medium, we should generate these types of vortices here. So we would expect some sinusoidal behavior if we look at the polarization as a function of the angle here. And indeed, this is what we see also experimentally, as indicated here by the data. But unfortunately, if we now go with the same intuitive assumption as before and assume the spins to be in equilibrium, this doesn't work out, because then you get something like the green line, which doesn't capture the magnitude and is also the opposite sign. And more or less recently, this behavior could also be explained, for example, by the group of Francesco and also by Yin, by including effects of the so-called thermal shear, which gives an extra contribution depicted here in red. And if you add both of these curves, you lie pretty much on the data. But from here, you can already see that this simple picture of spins that are equilibrated cannot be complete. Now, how do we usually put these kind of assumptions into equations? This is the Pauli-Lubanski vector in global equilibrium. I will say something about equilibria later. And there are two main things here. Okay, there's an integration over some hypersurface, preferably the Friesort hypersurface. And then you see two main things, which is why I colored them. On the one hand side, you put here some equilibrium distribution function, namely the Fermi-Dirac distribution function. So with this kind of formula, you neglect dissipative contributions. Secondly, and this will be my main focus in this talk, there is the thermal vorticity here, defined in this footnote. And this is precisely the assumption that the spin degrees of freedom are already in equilibrium. However, it's actually not really clear, on the one hand side, how fast the spin degrees of freedom equilibrate, and on the other hand, how dissipative effects influence the polarization. So I'm not going to talk about dissipative effects in this presentation, although it's also an interesting subject, but I will try to give some estimate for the answer to the first question, namely how fast the spin degrees of freedom equilibrate. Well, of course, this video doesn't work, it never works. But this is actually a nice comparison that I wanted to make. Because there are some other areas more or less in daily life where we can see something like this, that spins need some time to equilibrate, namely in nuclear magnetic resonance, which is used to do magnetic resonance imaging when you go to the doctor. And the technique there is that you apply a large constant B field, for example, in the Z direction, and then you apply an alternating field, in this case in the XY plane, so transverse to this large constant field. And what this does, and what you should have seen in this video if it would have worked, is that the spins of the particles go away from their equilibrium direction, so they get flipped to the transverse plane. And then when you switch off this alternating field, these spins will slowly relax back to the equilibrium value. There are two characteristic timescales involved here. They are usually called T1 and T2. T1 tells you how long the spin takes to reach back to its equilibrium value in Z direction, so to realign with the magnetic field. And T2 tells you how fast the magnetization in the transverse plane, so in the XY plane, decays. And in general, those are usually not equal. In equations, these are given by the so-called Bloch equations shown here in the lower right. So the lower one of these tells you how fast the magnetization recovers in the longitudinal direction, and the upper one tells you how fast the magnetization in the transverse plane decays. And basically, we are looking to obtain something like this, but for example, but of course not with magnetic fields, but with rotation as the driving force. So basically, we are trying to do something like MRI for the quark gluon plasma, and maybe get some cool pictures like this. Now, as Shi Pu already stated, we want to do this in a hydrodynamic framework, and hydrodynamics is usually based on conservation laws. I will, for this talk, abstract from charges, so we consider a system of uncharged fields, but the extension is more or less trivial. And in this case, we have two conservation laws that we get directly, namely, we should conserve energy momentum, and we should also conserve the total angular momentum. So the energy momentum conservation is given here by equation 1a. The energy momentum tensor has to be divergence-free. And equation 1b gives us the conservation of the total angular momentum. The total angular momentum can be split into a spin part and an orbital part that gives you the antisymmetric part of the energy momentum tensor, such that this also becomes a non-conservation equation for the spin tensor. Obviously, this is not a closed system, simply because those are 10 equations, so 4 and 6. But on the other hand, we have in principle 16 components in the energy momentum tensor and 24 components in the spin tensor. So something is missing, and what is missing is precisely the information about dissipative quantities, which has to be provided from somewhere else. For example, from some microscopic theory like kinetic theory, from a gradient expansion, or from whatever you will. And in this talk, I'm going to consider so-called ideal spin hydrodynamics, which I'm going to define in the next slide. But as a disclaimer, I'm going to use already some input that I anticipate from kinetic theory, which we will use later explicitly to really compute some coefficients. Now, what do I mean when I say ideal spin hydrodynamics? So this would be my kind of working definition. Ideal spin hydrodynamics is characterized by the fact that the conservation laws, together with an equation of state, completely determine the evolution of the conserved currents. What does that mean? Well, it means that we have to find some way to make this system of equations here closed. So we have to go from 40 quantities to 10 quantities. And then we have to, we can think about what the quantities at our disposal are. On the one hand, the symmetric part of the energy momentum tensor can be characterized, as we know from ordinary fluid dynamics, by an energy density or temperature, those are related, and a force velocity. The force velocity only has 3 degrees of freedom because it's normalized. So those are 4 quantities which correspond to these 4 equations here in 1a. The spin tensor, on the other hand, we have to find 6 quantities that characterizes the conservation of the total angular momentum. And we choose the so-called spin potential, which you can imagine as a thermodynamic conjugate to the to the total charge, which is given by the total angular momentum. The spin potential is an antisymmetric second rank tensor, and as such, we can decompose it like the Maxwell, like the field strength tensor, into an electric part that we call kappa, which is 3 components, and a magnetic part, which we call omega, that is also 3 components and is a pseudo vector. So with this, we have our building blocks at our hands. So we have 4 quantities for the energy momentum tensor, epsilon and u, and we have 6 quantities to build the spin tensor out of, namely kappa and omega. And before I go on, I want to say a few words about equilibria, because in general, we have 2 kinds of equilibria. On the one hand, what you usually consider in thermodynamics is so-called global equilibrium. In this case, the inverse for temperature, so the for velocity over the temperature, has to be a killing vector, so just to fulfill this equation. And on the other hand, the spin potential has to be equal to the so-called thermal vorticity, which is given by this antisymmetrized derivative of the for temperature. So in global equilibrium, our building blocks here, they're actually not independent, but the spin potential is determined uniquely through the for temperature. In this case, entropy is also exactly conserved. So yeah, it's exactly 0. On the other hand, there's local equilibrium, which simply relaxes these assumptions. So we do not have a restriction on the inverse for temperature, and we do not have a restriction on the spin potential. And in this case, entropy is not exactly conserved, but it has small quantum corrections. So it's roughly 0. And ideal hydrodynamics, and as such ideal spin hydrodynamics, should be based on the concept of local equilibrium, which simply means that we keep this spin potential here as a dynamic quantity, and we do not set it equal to the thermal vorticity, which is precisely what I referred to in the beginning. So we're not going to assume that the spins are in equilibrium. Now we can use our building blocks to build the currents that we want to describe. For the spin tensor, we simply assume that it's linear in the spin potential, and then we just write down all the tensor structures that we can find. And these are the most general tensor structures weighted by some coefficients that are called A, B, C, D, and E. And then we can go and decompose the spin potential again into its electric and magnetic parts, and we end up here with the 3rd and 4th line. These functions A to E are some functions of the energy density or the temperature, as you wish. And we have to fix them like an equation of state by some microscopic theory. Also, I should mention that these are not all independent, but if we demand, which we will do, that in global equilibrium, the spin tensor is conserved, so that the divergence vanishes, but only in global equilibrium, then there's a constraint on these coefficients, which basically looks like this. So only 4 of them are independent. The energy momentum tensor, on the other hand, we split into a symmetric part and an antisymmetric part. And then we're also going to construct those 2 from the quantities at our disposal. The symmetric part, we simply decompose as in usual fluid dynamics. So we decompose it with respect to the fluid for velocity, and we have a part with the energy density, and a part that corresponds to the pressure. The antisymmetric part, on the other hand, now this looks maybe a little complicated, but the intuition is actually very, very simple. So this here is simply the electric part of the spin potential. And the term with the thermal vorticity is the respective projection of the thermal vorticity, which means that it's simply the value that the electric part of the spin potential takes in global equilibrium. So in global equilibrium, this bracket here will be 0. And by the same logic, we have the magnetic part of the spin potential and also its value in global equilibrium related to the thermal vorticity. So this antisymmetric part of the energy momentum tensor is constructed under the assumption, which we will later on verify by our microscopic calculation, that it vanishes in global equilibrium. Also, I've put some factors of h bar squared here. Those are to signify that this is actually a 2nd order quantum effect, which will also be verified by our microscopic calculation later. But by now, we take it as an assumption. And these objects gamma kappa and gamma omega are simply some coefficients that we do not know for now. They are also functions of the energy density. Now from this, we can write down the equations of motion. But first, we should talk about the order to which we want to include quantum effects. Now, as you have seen, I've put some H bars here, which simply counts the order of the quantum corrections. And our goal will be to include the quantum effects to leading order, which means you want to just go to order H bar. But as I said before, the antisymmetric part of the energy momentum tensor is second order in H bar, which means that it will not play any role in the equation for energy momentum conservation. How can you see this? Well, you take the divergence of the energy momentum tensor, and you can see that those terms here of the symmetric part, they are zeroth order. They also appear in standard fluid dynamics. But the antisymmetric part is second order. So if we only want to include first order corrections, we can simply drop this term from the energy momentum conservation equation. On the other hand, we cannot drop it from the equation of motion for the spin tensor, simply because the spin tensor itself is already a first order quantum effect. So we can basically cancel an H bar on each side. And this system of equations here is pretty interesting, because the first one, the first equation just gives you the usually Euler equations of ideal hydrodynamics. And this means that there's no back reaction of the spin on the evolution of the fluid. So how you can solve this is pretty easy. You first solve your fluid in whatever kind of geometry or with whatever kind of initial conditions you want. And then you take the solution for your fluid, like the fall velocity and the temperature, and you use it as an input for the spin equations of motion. So it's kind of like a mean field theory. And it's simply an artifact of truncating the system at first order in the quantum effects. And given that we know that polarization effects are small, this should be hopefully rather reasonable. And okay, now since we can put in any kind of fluid geometry that we want, we start with the simplest one. Namely, we look at a fluid at rest. So we take the fluid fall velocity to be constant, just 1, 0, 0, 0 in some frame. We take the energy density to be constant, take the pressure to be constant. So everything is very easy. But still we can see some interesting behavior of the equations of motion for the spin tensor. And what we do now is simply we insert this form of the spin tensor that we constructed before into its equation of motion, and we apply some projectors to disentangle the electric and the magnetic parts. And what we end up with are equations 3a and 3b. Those already look nice, but they look even nicer if we simply go to the fluid rest frame, which is very easy because, well, the fluid is just stationary. So we move these 4 vectors here, kappa mu, to a 3 vector kappa, and we move the 4 vector omega mu to a 3 vector, well, omega. And what we end up with are equations 4. And now you can already see, aha, this looks at least a little like the Bloch equations that I showed before, which described the relaxation of some spin in a magnetic field. Namely, these are kind of relaxation equations, and they are coupled. And we can already anticipate that the relaxation timescales will be determined by these coefficients here, which I have appropriately named tau kappa and tau omega. Also, I should mention that these all these constants like A, B, C, D, E, and also the gammas, they are simply constants due to our assumptions on the fluid, because the energy density is constant as well. What is different here from the case of the Bloch equations that I showed in the beginning is that those equations are coupled. So actually they feature some interesting dynamics. And we can find this if we simply take, for example, the time derivative of the first equation and then insert the second one. You know, the usual manipulations that you do, for example, when you derive wave equations for electromagnetic fields from the Maxwell equations. There we can disentangle longitudinal and transverse components. So the longitudinal components, they are pretty straightforward. You just take the divergence of the equations I just showed on the last slide, and you get that the longitudinal components follow relaxation equations with relaxation terms given by tau kappa and tau omega. Nothing special to see here. The transverse components, on the other hand, so taking the time derivative of one equation, inserting the other, and doing some algebra here, will lead you to damped wave equations. And interestingly, you see basically there's 2 times the same equation, just one for kappa and one for omega. The waves travel with some speed of sound, cs squared. And there are some damping coefficients A and B, which are somehow related to these relaxation times introduced earlier. Now to connect with some earlier work, we can also see what happens if we let these coefficients gamma kappa and gamma omega. Remember, those characterize the antisymmetric part of the energy momentum tensor. If we let those go to 0, the damping simply vanishes and we end up with undamped wave equations, which was found in this reference 2 years ago. Now when we have a wave equation, we want to look at what the dispersion relation does. And I already said kappa and omega follow the same equation. So we just do some Fourier Laplace transform. This quantity x here can be either kappa or omega. Yeah, so we do a Fourier transform in space and a Laplace transform in time. And then we insert this into the wave equation and we get some relation for s as a function of k. And we basically have 2 branches, which are called s plus and s minus. And you can see for momenta, which are large enough, these waves start to propagate. So there's an imaginary part here. And for small momenta, they will simply be damped. Yeah, for k going to 0, you can actually see that the branch S plus goes to the inverse of the maximum of the 2 relaxation times, whereas the branch S minus goes to the inverse of the minimum of the relaxation times. So now if you think about this, okay, the maximum is the largest thing, so 1 over the maximum will be very small, so S plus, yeah, will be the smallest of the 2, which means that this is like this is the smallest damping, or rather the longest relaxation time. So at long times, the mode S plus will dominate. And because, as I said, the components kappa and omega fulfill the same wave equation, this means that the slowest relaxation time controls the damping of both of them. So even if one of the relaxation times is very short, if the other one is long, this will, due to the equations being coupled, result in both quantities relaxing very slowly. And I'm saying this, of course, because indeed this will be the case. Now this is as far as we can go with a macroscopic approach. Now we actually have to go and compute these coefficients. And as advertised, I'm going to do this from the basis of quantum kinetic theory, which I'm going to introduce in exactly 2 slides. So I hope it's not too dense. So this is the basic idea. You start with some quantum field theory. At this point, your objects of interest are operators. And then you move from there to a quantum kinetic theory. So to a limit where you can treat your wave packets as scattering quasiparticles, which works if your interaction length scale is much smaller than the mean free path of these quasiparticles. And then if your mean free path in turn is much smaller than the hydrodynamic length scales you're interested in, you can derive hydrodynamics from this quantum kinetic theory. Now, the first point is essentially what I just said. So we work in the limit that we can treat our wave packets as scattering quasiparticles and include quantum corrections perturbatively. And in such a theory, you can characterize the distribution function, the distribution of your quasiparticles through a distribution function f, which depends on position x, momentum k, and a continuous spin variable, which we call S. This distribution function fulfills a Boltzmann type equation, which you see down here. So on the left-hand side, you have the flow of this function in phase space, and on the right-hand side, you have a so-called collision term. These integrals d gamma, they integrate over both momentum and spin. The delta function just tells you that the momentum is conserved. W is a transition rate. And then we have the distribution functions here. So this is for binary elastic scattering. And the most interesting thing here is, of course, that these distribution functions are not evaluated at the same space-time point, but they are shifted by some quantities which we call delta, which are some non-local space-time shifts. And they tell you that your particles do not scatter at the same space-time point, but they are rather shifted some distance with respect to each other. And this is important because that is the mechanism by which microscopically spin and orbital angular momentum are exchanged. So we expect these guys to play some role in the coefficients that describe how the spin approaches equilibrium. Now, how to go from this to hydrodynamics? Well, we can simply take the conserved quantities that we're interested in and express them as integrals over this distribution function. The symmetric part of the energy momentum tensor is given by this familiar expression. So you have the flow of mu momentum in mu direction. The spin tensor, on the other hand, you can characterize as the flux of some microscopic dipole tensor given by this Levi-Civita and the momentum and this spin vector here. And the antisymmetric part of the energy momentum tensor, one can write like this, which is pretty interesting because notice that this square brackets here actually mean this is not one integral, these are 4 integrals, because this is a type of collision term actually. And it depends on the non-local shift that occurs in this collision. And now we need to insert some distribution function here, and then we can simply read off all of the coefficients that are interesting for us. Now we have to ask which distribution function do we insert. And as I said a few slides ago, we are interested in local equilibrium. So we insert the local equilibrium distribution function, which is characterized by the fact that it makes the local part of the collision term vanish. This is the local equilibrium distribution function. There's a 0th order term given by the usual Boltzmann factor. And also there's a first order correction. You see first order H bar, so this is our quantum correction, which depends on the spin potential. And now we simply take this one, equation 12, we insert it into the conserved currents, and then we can read off everything that we want. And here's the result. So tau kappa, tau omega, and these coefficients mu are given by this. So these quantities I 3, 1, for example, this is some thermodynamic integral. This is rather easy to compute. And these quantities gamma kappa, they are related to the antisymmetric part of the energy momentum tensor. They are given by some collision integrals. I don't want to write down the whole expression. They're rather long, but you can compute them as soon as you specify some interaction. Before we do that, I just want to point out that this shows us explicitly that non-local collisions cause the relaxation of the spin potential towards thermal vorticity. As I said, this should not come as a surprise because that's the microscopic mechanism that exchanges orbital and spin angular momenta, but it's still good to see this explicitly. Now we need to specify some interaction, and I choose the simplest one, which is this kind of 4-point interaction. Yeah, we have some coupling strength G, and then we have simple 4 Fermi interaction. Unfortunately, I do not know what G is, so I'm not going to give some absolute values for these relaxation times, but rather I'm going to express these relaxation times as a function of the relaxation time of the shear stress tensor, which you can also compute in this setup. It's a dissipative quantity, which I didn't introduce before, but you can do it. And this gives you an idea of how large the time scales of the relaxation of the spin degrees of freedom are with respect to the typical dissipative timescales of the system. And this is the result. So we have these relaxation times as a function of mass over temperature. That's the only dimensionless quantity basically in our system. And we can see that this quantity tau kappa, it actually remains, I think it starts at roughly 0.7 or so times tau pi. So it's on the order of the timescales of the dissipative degrees of freedom, and it stays there over a large range of values. Tau omega, on the other hand, starts at roughly 2 times the relaxation time of the shear stress tensor. But then after the ratio of mass over temperature reaches 1, it starts increasing pretty rapidly, and actually it increases with m over t squared. So what this tells you is that if this ratio, mass over temperature, is not too small, that actually tau omega can be very large compared to the dissipative timescales in the system. And this in turn tells us that the process of this spin relaxation is actually a comparatively slow process. So it's important to not consider the spins as equilibrated, but to also take a closer look at the dynamics. And with this, I come to my conclusion. So I've shown you that in ideal spin hydrodynamics, the components of the spin potential fulfill damped wave equations. These damping factors are controlled by the relaxation times of the system, and the slowest relaxation time controls the damping of the waves at large times. And these relaxation times can be computed from some microscopic theory, which we chose to be quantum kinetic theory. And while one of them is on the order of the dissipative timescales of the system, the other one can be really large, depending on the value of mass over temperature that you have. And this implies given that the value of mass over temperature is not too small, one has to treat the spin potential as an independent dynamical degree of freedom. And the assumption that it is always in equilibrium is not really justified. Thank you for your attention.
Okay, thank you so much for your presentation, David, and also for Bruce. So now it turns to the discussion part. I already saw some discussion on the chat box. So Mekanisa, can you speak out and ask your question?
Okay. Thanks to both for really interesting talks. And I guess I always have the same dumb question, which at this point I should know, but anyway, you can help me out. Always in these cases, one really has to be thinking of both particles and fluids at the same time. And I guess I've been trained from the old days to be thinking that these are different, that fluids are not particles. I mean, I shouldn't think of them at the same time. Maybe I'll ask, and I know that Masoud has some answer to it. On slide 4, the mass that is in the formula on this page, on your slide 4.
Yeah, 1 second. 4. This one? I think you mean this one, right? 3.
I do. I suppose that's right. This mass M is what?
Mass of the hadron.
In this case, this mass is the mass of the hadron.
Okay, that's to me surprising. I mean, am I thinking of a system where the hadrons, as opposed to inheriting their properties, which include spin, but also baryochemical potential charge and so forth, from the fluid, that they are also interacting with the fluid, and that's what leads to the polarization?
I think this is a very interesting conceptual point. So the way I think about this is that this is the mass of the hadron simply, because that's how you get compute the polarization from some distribution function. But inside your simulation, when you actually look at the spin degrees of freedom, I would say that one should use a different mass. So this might be the mass of the hadron, but when I go inside inside the kinetic theory, say for example this mass that appears here in these coefficients, I would say that this is not necessarily the mass of the hadron. So my best guess so far is that this type of mass that appears here for these coefficients is maybe some kind of dressed quark mass, and then one kind of ignores the process of hadronization. It just puts the hadron mass at the end when you use your final fluid variables to compute the polarization of the particle that you want.
Okay, thanks for that. So I'm thinking of a fluid of particles, or at least actual particles, quasi-particles, I don't know, that exist during the evolution, and that leads to this distribution function F. Yeah. But then at the end, it really is the hadrons at freeze-out which inherit their properties from the fluid cell that's from which they're born. Is that the right thing? So it's two different masses.
That's how I think about it, but I see already two comments.
You should not worry about the hands, David.
Yeah, but that's how I would think about it. Yes.
Okay,
I'll listen. Lisa, does that answer your question?
Sorry.
Well, I'll be maybe. I actually have another question too for later, but I bet it sounds like other people have input too, so I'm going to listen closely.
Maybe Wooly first, if
to this question. I mean, the equations that you pointed to were derived in a context where the fluid is microscopically describable as an ensemble of particles described by kinetic theory, and so it's in such a picture where you know the constituents that make up the fluid, then you know what the mass should be. And maybe at early times, this should be the mass of the relevant quasi-particles then, which may not be lambdas and phi's and so on. But at freeze out, it should be the hadrons that you are measuring. Maybe just that as a comment on what the M stands for. But without a picture that gives some microscopic interpretation of the hydrodynamic or some microscopic substructure to the hydrodynamics that is based in kinetic theory with quasi-particles with well-defined masses, the M doesn't make any sense.
Mhm.
Yeah.
Right. It makes sense, the freeze up.
Yeah, that M makes sense at the freeze out.
And I saw Lorenzo raise his hand, but I assume that Masson will first also will make a comment on this discussion. So if so, Masson, can you also speak out? Sorry if I didn't pronounce your name correctly. Masson, is that the right pronunciation?
It's okay, Masood, but
Masood, okay, sorry for that. You want to contribute to this discussion, I assume?
I just wanted to, I mean, because I wrote something short. Can you show slide 10, please, David?
Yeah.
So actually, this question that Mike asked, I think it's very important. I mean, this is something that we were always discussing about, that even in the kinetic theory, because in the usual, for example, in the DNMR, these kind of things do not actually appear out of the transport coefficients. So, I mean, so you have some transport coefficients there that you can, okay, so you say, okay, the form of the equations, hydrodynamic equations remain the same, but I have another microscopic theory that doesn't have the quasi-particle picture, so I can put something else, which is the thing that usually people do. But here, after this work, I started to think that, okay, you can think about fluid and a spin because of this equation 2A as two different, two separated kind of systems. It's like, I mean, I'm just not very seriously, but you can think of it as a kind of mixture. So the picture that you can apply to the fluid itself doesn't need to be a picture of quasi-particles, but the spin you can effectively have this kind of picture. So because you are going to solve equation 2B after solving equation 2A, and then you use the 2A as an input to 2B, so you don't need to mix two pictures. And another thing that writing the equations, I mean, S lambda mu nu in terms of A, B, C, D, E, that I liked a lot because you can also use other kind of, I mean, you can just assume some kind of conformal system, which we entertained, I mean, recently, and not using kinetic theory on everything. I mean, you just somehow assume that there are just some temperature dependent coefficients. So then you don't need the quasi-particle picture.
But can I just quickly ask a question? But this is the spin of what? Spin of gluons? Spin of quarks?
Yeah, exactly. That's it. I mean, that's but you should be somehow at this level. I mean, you should be somehow agnostic to what is spin of that is spin of what. Of course, if you want to simulate and you want to find the results, you need to think. I mean, it's not easy.
Yeah, exactly. So as Masood said, so up until say this point here, or say this point, this is general. So there's no mentioning of like what is actually what the fluid is composed of. And then just to actually compute these transport coefficients, we have to put some microscopic theory, which we take kinetic theory because we know how to do it.
Can I just jump in? I'm sorry. It might one could be agnostic with the equations because there's whatever with that, but I'm trying to think conceptually here, and it's certainly not going to be a fluid of pions, is it? Because they're spin zero. So does it really not depend at all on the particles?
Okay, okay. If you don't have any spin, then yes, of course. Okay, that's right. So the particles should have the spin in the first place.
Does it matter how much spin? I mean, zero doesn't sound very good, but how about a spin 3.5? Does it not care? Are we really agnostic?
That should work. I mean, every kind of microscopic field that gives you a non-vanishing spin tensor should work. So I would say everything apart from, say, scalars should yield at least like a non-trivial result. For example, for spin 1 particles, you would also have like a spin tensor, but you would also have some more degrees of freedom related to the other components of the spin density matrix. Those are not included in the conservation equation. Like for example, the alignment or the tensor polarization. These are components that are not included in the spin tensor. So these would not fall under this kind of thing. So this kind of discussion is. This does not say anything, for example, about the dynamics of alignment, if you're interested in that.
Okay, good. I think, Lawrence, are you still there? And can you speak out and ask your question?
Hello.
Hi, Lawrence.
Thank you very much.
Yeah.
Thank you for the wonderful talks. I learned really a lot. I have a mathematical questions, one for each speaker. So I will start with David since we are here. Could you please go back to slide, I think it's slide 10.
This one?
Yes, this one. Okay, so I have a mathematical question here.
Uh-huh.
So let's imagine a situation where we start with 0 angular momentum, but we have some spin, okay? So spin is order h bar, okay?
Yeah.
Then the spin wave is damped and is converted in orbital angular momentum. And if I understand correctly what you're saying, the spin wave can be damped completely.
Yes.
Which means that eventually there will be an orbital angular momentum of order h bar. Which means that there is a problem in claiming that there is no back reaction of the spin on the fluid.
Yeah, so you're referring to the Francesco, you already said it. Which one is it? The Einstein, the
Haas effect.
Yeah, so that when you magnetize it, it starts rotating. So from the way I see it, this is probably not included in our description precisely because this kind of back reaction is not there.
But I think there is a problem because this effect is of order h bar, and the question and you're throwing them away. So my belief is that if you look at equation 2b, the additional h bar is a timescale effect. Okay. But if you look at sufficiently long time scale, then you get that we can talk about it in more detail later. But I think that there is a problem because if you say that the spin is of order h bar, and then there is this effect by which the spin becomes orbital angular momentum, then you have orbital angular momentum of order h bar. But in this equation, you are neglecting the Einstein-de Haas effect, or I don't remember which one of the two. Yeah, I think you're neglecting the Einstein-de Haas in this framework.
Yeah, that's a good point. I don't think I have a direct answer to that.
Yeah, I think I know. I think it's along that when you take the limit as h bar goes to 0, you are sending the time scale of the Einstein-de Haas effect to infinity. And this is why you don't see it. But then I would expect this to appear also in the damping of the waves. So we can look at the math if you want later. But I think that this must be resolved because it looks like an inconsistency otherwise.
Yeah, I don't have a direct answer, so we can for sure talk about it later.
Yeah.
What I can say is that if you go at it from the Masoud maybe as an answer, but what I can tell you, if you go at it from like the microscopic point of view, then the power counting is actually very clear. So for example, for the energy momentum tensor, you get basically 1 power of h bar from the non-local part. That's one of them. And the other one comes from this difference here, which is also first order in h bar. So there, from that side.
Yeah. So yeah, exactly. So I believe that the Einstein-de Haas effect will, if I understand correct, should occur over order h bar, and one h bar is because the spin is h bar, and the other h bar it means that it's suppressed. The time scale is it takes long over a factor that tends to infinity as h bar goes to 0. But you see, the exchange of angular momentum in total is an amount h bar when you integrate over all the time, because once the wave has decayed, you have transferred an h bar, an order h bar 1 to the orbital. So eventually I expect it to be if you look at over super long time scale, it becomes again an order 1 in H bar, if you understand what I'm saying.
Maybe.
Yeah, we can try to make it rigorous.
Okay.
So
do you want
if
to
I
comment on
can,
this?
yes, sorry.
Yeah.
Oh.
You want to ask also a question for Pu?
Yes.
Please.
So I have a question for Pu. I just would like to understand one point. So you compare the thermodynamic stability analysis with the linear mode analysis. So I just would like to understand, do you think that it needs to be proven that the thermodynamic stability analysis implies the mode analysis? Because in my head, I have a proof, and I just would like to understand, because I was a little bit confused about the philosophy of how you draw the comparison.
Okay. Thank you for asking. So actually, when we find out the thermal stability condition, I mean, I should say in this way, if we have the stability condition in a linear mode analyze, we can get the thermal stability condition. But the opposite way is not true. We cannot be true. So that means the thermal stability condition is more stringent than those divided from the linear mode analysis. I think this point is agree with what you find in your paper.
Okay.
That means the thermal stability condition should be equivalent to the linear mode analysis, or more stringent.
No, my question is just, do you think that we need, in the fully general case, a proof that thermodynamic stability in general implies linear mode stability? I mean, do you think that there is the need of this proof or not? Because I can give you if you're interested in it. Yeah.
Oh, okay. That will be great. Yeah, that actually
okay.
we are thinking, but but we didn't get the exact answer. Yes. Thank you.
Okay.
Yes.
Okay. I will send you. I will send you some notes.
Later. Yes.
Yeah. Okay. Thank you.
Thank you.
Great. Yeah. I saw Lisa may want to still say more, but before that, I'm curious if there's any other question from the audience.
May I ask a question?
Yeah, please, Francesca.
Yes, so sorry. I mean, I raised my hand physically because you can see me. Well, I must say that these online seminars have actually improved recently. So I had really impression to be here. I want to ask you a question to Shi Pu. And the question.
Oh, yes, please.
Yes. Yeah. Can you hear me?
Pu, do you want to put to sharing the screen by any chance?
So the question is the following. So I wanted to ask you whether the pseudo gauge invariance or non-invariance so has had some effect on the constitutive relations that you have, say, found for the spin tensor.
You mean the causality condition? Well, the causality condition be
No,
modified.
I mean, so the question is whether if you change the spin, so how? So let me rephrase the question. Is how dependent the relations that you have found eventually are on the choice of the spin tensor.
Okay.
And then I'm asking
this is I have to.
Okay. Yes, please.
Yeah, I think this is a very, very good question. So actually, so we when we're doing this work, we are also thinking what happened in the Benefanti form. What is the causality and the stability conditions? While try thinking this, but so far we don't have a clear answer to it. Honestly speaking, we are computing it. But probably you remember, if we take the pseudo gauge transformation to the spin hydro, the whole expression become very different, right?
Yes.
So the analyze for that kind of is it's completely different. Yes, but we are doing this. So far, we don't have the clear answer to this question. I'm sorry. Yeah.
Okay. No,
but this is a very important question. Yeah.
Okay.
Yeah.
Thank you. No, I'm saying this because
Thank you.
recently we also studied the shape, the form of the divergence of the entropy current, and we found out that this also changes. It's affected by pseudo-gauge transformations. So not just the form of the entropy current, even the form of the divergence.
Yes.
Yeah.
Yes, we have read your paper, your cooperation with Xinli and other cooperators. Yes, we know that paper. Yeah. You have find something very important for the entropy after the pseudo-gauge transformation. Yes.
So I was wondering whether if you change the spin tensor, then you get some different causality or thermodynamic stability bound, something like this. Okay, so you are doing this. Yeah, this is what you're saying.
Yes.
Okay. Thank you.
Thank you.
Any other questions or any comments related to Francesca's question? So maybe I want to ask actually a brief conceptual question also related to the instability, because usually when we are talking about the instability, we say that we perturb the system by changing, give some linear perturbation in energy density, and the stability means the energy perturbation will decay. But my question is it physically acceptable that we do the perturbation also in spin degree freedoms? The spin degree freedom will grow, but the total energy are still decay. Any perturbation from the energy set is decay. Is this still a physically acceptable or stable situation? Do we still need to require that the perturbation in spin will decay? So that's my question. So I assume when you are talking about the stability criteria, you also assume the perturbation in the spin degree freedom will decay. But my question is it now that my spin perturbation grow as far as my energy perturbation decay, this is a physically sensible situation in the linearized region?
Maybe I say something wrong, but in my point of view, it doesn't matter you perturb the energy density or the spin density. So if this is increased with time, that means, for example, if you do some simulation, you have some errors. So that errors actually increase with time. So that actually means the simulation is unstable, or the result is untrustable. So that is why we require all the quantity the fluctuation should decay with time.
Okay, maybe Lorenzo.
I don't know whether I answer your question.
Perhaps I can give you my perspective. So the idea is there is a state that we call thermodynamic equilibrium, that is the state that minimizes the free energy. And there you know from thermodynamics that it cannot change in time and that it is stable under perturbations and fluctuations. You take the thermodynamic equilibrium state, you impress a little kick, depending whether you're in a bath or not, there may be some constraint on conservation of energy and so on. But in the end, the point is the system wants to go back to the state of thermodynamic equilibrium. So in my understanding, the requirement that a theory be stable is just the requirement that the thermodynamic equilibrium state of the theory has this property that we know comes from statistical mechanics and thermodynamics. So if you want, I would call it a consistency check with respect to an underlying statistical mechanical description or thermodynamical description. Of course, you can imagine a situation where you create a stationary state that is unstable against spontaneous generation of spin, spontaneous change of spin, but that wouldn't be the thermodynamic equilibrium state. That would be a stationary metastable state that you have engineered, but that the system under fluctuation will spontaneously depart from. I don't know if this is the satisfactory answer.
Maybe I think we really need a more detailed discussion, maybe even some workshop in person. But thanks for your comments. So I think we are closing to the end of the seminar, but I still think maybe Lisa, can you just briefly ask your question and then we can close today's discussion.
Okay, it was kind of just a follow-up again to David, and maybe I already have my answer, right? One thing you mentioned at the end is the spin alignment of the vector mesons, which has come up. It seems that no matter what, the spin 0, spin 1, spin 3 something like this, of the quasi-particles, you would then get a prediction for the spin alignment of the phi. And that number that you would predict would depend on not only the mass, but the spin of the quasi-particles. Am I correct? So even quasi-particle with spin 0 would still give a spin alignment of the phi.
No, I mean, if you would, so I think one has to disentangle which assumptions one puts where. If you look at the polarization, right, you are considered with this with the Pauli-Lubanski vector here. If you are considered with the alignment, you would have a similar expression that also has some integration over the freezer type of surface, right? And it would have some other fluid quantities in here. For spin 0 particles, this object here would be 0, and also for spin and also the alignment would be 0. Because you can derive a relation like this from the underlying Wigner function, and then you have some component of your microscopic Wigner function, which is related to the actual spin of the particles in the fluid, and that you can then you can put some hydrodynamic approximation to get an expression like this. What I said was, or what I meant was independent of these kinds of assumptions, is when you consider just the hydrodynamic equations. So you consider equations, for example, 1a and 1b, and then you do this kind of construction that you think, okay, what can be there, and you do this, this kind of program that I showed here. And at that point, there's no mentioning of which particles you have. But
if I may jump in, I think what you're saying is that as long as the system can be described in terms of quasi-particles, you cannot have alignment without having quasi-particles that have at least spin 1. If the liquid is not, if you give up on the condition that the liquid can be described in terms of quasi-particles, you can have spin alignment, but you will not have such an interpretation in terms of a spin of particles. It would come from somewhere else. I have no example to show you how to do that. But hydrodynamics is in that sense more general than the kinetic theory, which refers to a specific class of particles.
Exactly. Thank you. This was exactly what I wanted to do. That was what I wanted to express. So better than I have worded it. So yes, exactly.
So in principle, you may have eventually spin alignment, even if the fluid is whatever. Can be done can be made of anything, and that because the spin alignment is a property that you calculate at the end when you hydrolyze.
Exactly, but if you have this kind of kinetic description, then well, no.
If you have a kinetic description, then it depends on whether these particles survive the hydrolyzation for it or not. If you can describe the plasma in terms of quasi-particles, you can describe the plasma in terms of quasi-particles, spin 1, spin 1/2, spin say 0.
Yeah.
But eventually, then you will have to to make calculation in terms of hadrons. So then well, you may have, in principle, for instance, you may have a spin alignment of spin 1 mesons, even if you had not spin 1 in the fluid.
Right.
Or quasi-particles in the fluid.
You can even have scalar quasi-particles, I think you're saying, Francesco.
Yes, exactly. Yeah.
I think so too, yeah.
Good. I think maybe we should let Rajaf to ask the last and a brief question.
Yeah, I have one small question. Thank you, David and Shi Pu, for the nice talks. My question is related to Shi Pu's slides, where you showed one space-time light cone diagram of fluctuations, one going inside the light cone and other going outside the light cone. And you said that the fluctuations, when you go outside the light cone, the time will be lesser than the time in the light cone. But did you consider the randomness of the fluctuations? Means how random the fluctuations are? Because in one of the recent works, if you consider the probability of going outside the light cone much lesser than the light cone which is going inside, the fluctuations going inside, then even though you will not have the covariant equations, it will never go outside the light cone because of the low probability. So I just want to ask how you consider the randomness of going, what is the probability of going outside the light cone?
Sorry, sorry, let me share the screen.
The slide number 33, I think.
So yeah. So you mean this slides, right? This one,
yes,
right?
Yes.
So here I just want to say, if you have some propagating out of the light cone, then you can always find a special frame. In that frame, this t becomes smaller than t0, because this is from the relativity. Relativity it can always find such a frame. But in that frame, actually, you look at the small fluctuation just increase with time. So that is physically unstable. So that is what I mean here. It seems your question referred to how to find that kind of frame, right? That is a different different question. I think we can always find something. This kind of frame should always exist.
My question is okay. Let me just repeat what I'm saying. So my question is, since the fluctuations are very random, so what is the probability of going of the fluctuations going outside the light cone? Means how do you know that there will always be some events for which this will happen?
Okay, I see. Here we didn't consider a random fluctuation. We just this fluctuation means we put something like a plane wave fluctuation to, for example, energy density. Then we expect its decay with time. Then there are two different scenarios. One is inside, it happened inside the light cone. Another one is it propagating out of light cone. So that is our assumption. And my conclusion is, if you happen in the second scenario, it will make the system unstable. So that is my logical. If I didn't answer your question properly, maybe we can discuss privately by email or discuss online.
Right. So I also need to, So I would like to first thank all the speakers and all the participants. And as Francesca said, our seminar is improved. So I'm wondering, so I hope we can also see you again in the coming seminars. So Daniel, do you have any announcement at this point?
So I'll send an announcement for our next seminar 2 weeks from now, shortly.
Do you have anything you want to announce at this point?
Nothing to announce. I'm still organizing the speaker, but I have a topic.
Okay.
It'll be related to the critical point in the QCD phase diagram from various different approaches, lattice and other approaches. And so I think with that, I look forward to seeing you in 2 weeks. And I want to thank David and Shi Pu again. And thank you, Yi, for chairing and for the wonderful discussion today. So thank you, everyone.
Okay.
I'll go ahead and close it there, and I'll see you in 2 weeks. Bye, everyone.
See you.
Thank you.
Bye.
Bye.
Bye.